Okay, so today we're going to be talking about radioactivity, and more specifically, I guess, the radioactive decay of a nucleus and what causes a nucleus to kind of undergo radioactive decay is if it's got an unhealthy, ratio of protons and neutrons, it's going to be unstable, and so it'll emit a high energy particle in order to kind of reach a more stable state. And this table kind of explains that a little bit more. As you can see, it shows the ratio of protons to neutrons, and the more protons you have, the higher ratio of neutrons you need to kind of stabilize the nucleus and stabilize that positive charge. And so, depending on where this or a certain atom is on this graph, whether it's below or above, it's gonna undergo some form of radioactive decay to get back, towards that kind of pink, stable, healthy nuclei area. And so, there's three different forms of radioactive decay that we're going to go over today that can kind of help adjust this balance. The first is alpha decay. As you can see there, it's just 2 protons and 2 neutrons ejected from the nucleus, and you'll see it written as the alpha sign, or you often just see it written as a helium nucleus. Important things to know about this is alpha decay is positively charged, because of the 2 protons, and then it's also fairly large compared to the other types of radioactive decay, and it's also a little bit lower in energy compared to the other types as well. Not that it's completely safe. You don't want to, expose yourself to this 24/7, but something as thin as a piece of paper can stop, the alpha particles. The next form I want to go over is the beta decay. And beta decay is special because it has the book goes over 3 different types of beta decay. So the first one I'll cover is electron emission. And the important thing to know about electron emission, it is the most common form of beta decay, and so it's often depicted with this sign, with just the beta negative. And the way this changes the nucleus is, so an electron is being emitted essentially from the nucleus, and so the nucleus is now less negative or more positive. So you have a nucleus that was turned into a proton because an electron was emitted. The next form is called positron emission, and again, it is exactly what it sounds like. The only difference here is that this time you're emitting a positive particle, and so the nucleus is going to be slightly less positive or more negative. So you're going to get a proton, gets turned into a neutron, and then you can see here you have that positive particle. And again, both of these, they do have mass, but they're much smaller when compared to a neutron or a proton. And then the symbol for this is just beta plus. The final type that the book goes over is electron capture. And again, fortunately, it's exactly what it sounds like. An electron just enters the nucleus and kind of fuses with a proton and gets turned into a neutron. Important things to note with this is that with electron emission, the atomic number actually goes up. You're getting an extra proton, where the other two types, your atomic number is going down as you have a proton that's turned into a neutron. There's not really a symbol necessarily used for electron capture. They might use EC. You might have to understand that, but often they'll just kind of explain, if this goes through electron capture, what's going to end result to be. The final type of radioactive decay is the kind of highest energy form, I guess, kind of the most dangerous, most likely to cause us humans harm if we encounter too much of it. And it's gamma. It's unlike alpha and beta, which I should have mentioned as well, that beta particles are usually negatively charged, not always, but for the most common type, you're usually going to see a negative particle. But gamma is not charged, it's neutral, and nor does it have any mass. It's just a photon. It's basically just kind of light energy. And gamma energy results from when electrons, neutrons, and protons kind of drop into a more stable energy level. Let me explain that a little bit better. So I'm sure most of you are familiar with the idea here that, you can have an electron and then a photon will come along, hit it, and it'll excite the electron up into a higher energy level, like that. But after a while, this electron is going to drop back down, and when it does, it's going to release a photon, the exact same energy that it absorbed. And so gamma radiation is, similar to this idea, but the thing the book kind of stressed is it's not only electrons that can kind of produce photons, but neutrons and protons can do the same thing. They can enter an excited state and drop down and release photons. And so that's why you often see that gamma radiation is kind of a side product of alpha and beta. It kind of happens as well when you have those types of decays, just because, when reactions happen, you often find it's more likely for certain parts of an atom to be in an excited state. And so it's just a higher probability of proton or neutron being excited and being capable of dropping an energy level to release gamma radiation. Okay, so I want to go over a problem real quick of the sort of application that you're going to have to, use this knowledge for. I only have time to do alpha, but just remember that beta and gamma are going to be fairly similar, except that with gamma, you're not necessarily dealing with change in masses, but rather just change in energies. And then beta, the change in mass is not going to be so much due to the electron as it is, just the change in charge. So I'll go down real quick. Let's see. So the question here is, find the energy emitted in the alpha decay of plutonium-239. And so how you're going to see a lot of these problems written is you'll have, the mass of the atom over its atomic number, which for plutonium is 94. And like I said, it was alpha decay, so I'll write that down as 4 for 2 helium plus, and again, this is all kind of ties into the conservation of mass idea, which gets a little bit contradicted later on, but from, this far away, that these big numbers kind of have to, that what's on the right side here has to add up to what's on the left. So you have helium plus, let's see, so 4 plus 235 is equal to 239 there, and then 2 plus 92 is equal to 94, and so you're going to get uranium here on this side. And so the way we can find the energy emitted by alpha decay is we need to find the change in mass that occurred here. And yeah, I know I just said that, these two things kind of have to add up to equal this. And while they do, there's a couple decimal points down where the mass actually changes a little bit, and where the exact mass of plutonium does not equal the masses of helium and uranium combined. And so the way we can find delta M in this case is simply, just the mass of plutonium minus the mass of helium plus the mass of uranium. I guess I should put those in parentheses. And fortunately, some very smart people decided it would be a good idea to just figure this out for us and put it in a table, so we don't have to find these numbers by ourselves. We just kind of got to consult the table in the book, and we know the mass of plutonium is equal to 239, sorry, 0.046526. And they give us the units in AMU, which I know may seem like a pain right now, but it actually comes in really helpful later. And then the mass of helium is equal to 4.002602. And then you have the mass of uranium, and that's equal to 235. Sorry, I forgot to label the units here. Okay, yeah, so uranium was 235.043924. 3924. Okay. And so when we calculate this delta M, if you plug this in, you're going to get delta M is equal to 0.000561 AMU. And so the equation that helps us relate mass to energy was given to us by Albert Einstein, and it's M equals mc squared. So normally you can see why having U would be a huge pain of trying to plug it into this equation, because you're not going to get joules if you plug in AMU. But fortunately, someone figured out this ratio that says that 1 AMU mass is equal to 931.5 mega electron volts divided by the speed of light squared. And so we don't actually have to change this. We don't have to go through, moles to find, kilograms. We can actually simply just plug in this, and it'll give us nice clean units that we can use to kind of figure out how much radiation we've been exposed to. And so if we plug in this number into here, you're going to get 0.005631 AMU times the speed of light squared. And then using dimensional analysis, we can say times, and we're basically timesing this by 1. We're just changing the units. If you have a hard time with dimensional analysis, it might be a good idea to refer to like a Khan Academy video before going over this. But you get 1 AMU under 931.5 mega electron volts divided by speed of light squared. So AMU, you're going to cancel, and you're also going to get speed of light squared canceled, and you're going to result in mega electron volts. And if you times these two numbers out, you're going to get energy is equal to 5.25 mega electron volts. And like I said, it's just a much more practical form of energy, or units of energy that you can kind of use to see how much someone's been exposed to. And that's all we have time for. But like I said, the gamma and beta problems are all very similar. You just want to remember that the mass of an electron is not calculated in to this part, in the change in M. So even if, you write it out, it's not necessarily going to change the mass enough to be significant unless the question tells you otherwise. And then same thing with gamma. It's just energy, so there's no mass in that equation.